Welcome to Scalable Data Processing in R.
I'm Michael Kane, an assistant professor at Yale University.
And I'm Simon Urbanek, an R core member and lead inventive scientist at AT&T Labs Research.
With the advent of big data in every field, you may need to analyze increasingly large data sets. In this class, we'll teach you some of the tools and techniques for cleaning, processing, and analyzing data that may be too large for your computer.
The approaches we'll show you are scalable in the sense that they are easily parallelized and work on discrete blocks of data. Scalable code lets you make better use of available computing resources and allows you to use more resources as they become available. When you create a vector, data frame, list, or environment in R, it is stored in the computer memory, RAM. RAM stands for Random Access Memory. It is where R keeps variables it creates. Modern personal computers usually have between 8 and 16 gigabytes of RAM. Datasets can be much bigger than this, though. At AT&T Labs, we routinely process hundreds of terabytes of data in R.
In this course, we won't process datasets that big, but we will show you some of the tools we use to create analyses that can be run on datasets that may be too big for your computer's memory, but less than the amount of hard drive space you have available.
According to the R Installation and Administration Manual, R is not well suited for working with data larger than 10 to 20% of computer's RAM. When your computer runs out of RAM, data that is not being processed is moved to the disk until it is needed again. This process is called swapping. If there is not enough space to swap, the computer may simply crash. Since the disk is much slower than RAM, this can cause the execution time, which is the time needed to perform an operation, to be much longer than expected. The scalable solutions we'll show here move subsets of data into RAM, process them, and then discard them, keeping the result or writing it to the disk. This is often orders of magnitude faster than letting the computer do it, and it can be used in conjunction with parallel processing or even distributed processing for faster execution times for large data.
If the computation you want to perform is complex, meaning it involves many operations, each of which takes a long time to perform, this can also contribute to execution time. Summaries, tables, and other descriptive statistics are much easier to compute compared to tasks like fitting a random forest. By carefully considering both the read and write operations and the complexity of the operations you want to perform on the data you have, you'll be able to reduce the effect of these bottlenecks and make better use of the resources you have.
In the first set of exercises, we are going to benchmark read and write performance, as well as the complexity of a few different operations in R using the microbenchmark package. A simple example is shown here. We use the microbenchmark function to benchmark the runtime of two different expressions. The first one creates a vector of 100 random normals. The second expression creates a vector of 10,000 random normals. The function returns a summary of the distribution of the runtimes for the two different expressions. The mean runtime for the second expression is about 20 times that of the first. Your turn to practice.